And dear students, in the chapter of complex stresses and strains, today's topic is Mohr's stress circle. I, Dr. Balraj Singh Brad, am presenting the topic. As discussed, for a point diagram A, B, C, D, under a biaxial stress system means direct stress along x-axis sigma x, along y-axis sigma y, and shear stress on this plane BC plane is tau naught positive because it makes a clockwise couple. Shear stress multiplied by area makes a clockwise couple about a point inside. So the sign convention is same as we have taken for the derivation of an analytical method. For the present, sigma x will be positive because tensile, sigma y positive because tensile, tau naught is taken to be positive if on BC plane it makes a clockwise couple. We have taken. Otherwise, if the sigma x is compressive, take negative. Sigma y compressive, take negative. If tau naught here is, this arrow is upwards, then it will make anti-clockwise couple, take to be negative. Then for any plane, oblique plane, KL subtending theta angle, which is anti-clockwise with DC plane, horizontal plane, or CD plane. For CD plane, KL is making an angle theta. Direct stress is sigma n and shear stress is tau. Relation is sigma n is sigma x plus sigma y by 2 minus sigma x plus sigma y by 2 cos 2 theta plus tau naught sin 2 theta. And tau is minus sigma x minus sigma y by 2 sin 2 theta minus tau naught cos 2 theta. We have derived these relations. We can find out direct normal stress and shear stress for any oblique plane for an angle theta made with the horizontal plane or CD plane. It is to be remembered. We can also find out principal stresses and their position and maximum shear stress planes and their positions analytically. Now we are going to learn about Mohr's stress circle, which is a graphical method. First, about the equation. Same relations of sigma n and tau. In these relations, let us substitute sigma x plus sigma y by 2 as A and sigma x minus sigma y by 2 as B. When we substitute this becomes A and sigma x minus sigma y by 2 becomes B. Similarly here sigma x minus sigma y by 2 becomes B. When we solve these equations become sigma n is A minus B cos 2 theta plus tau naught sin 2 theta and tau is minus B sin 2 theta minus tau naught cos 2 theta. Now if we take A to the other side, sigma n minus A, and let us square these two equations and add, then left hand side will be sigma n minus A whole square plus tau square, and right hand side will be minus B cos 2 theta tau naught sin 2 theta square, this terms whole square, plus minus B sin 2 theta minus tau naught cos 2 theta square, this terms whole square. When we open this right hand side, we will get B square cos square 2 theta plus sin square 2 theta tau naught square sin square 2 theta plus cos square 2 theta. Now this will be Sin square 2 theta plus cos square 2 theta will be 1 here and here, or the equation will be sigma n minus a whole square plus tau square is equal to b square plus tau naught square. This is an equation of a circle. We will discuss next slide. We have derived this relation sigma n minus a whole square plus tau square is equal to b square plus tau naught square. Now b is given sigma x minus sigma y by 2. Tau naught is the given shear stress. So this right side is a constant and we can substitute it to be r square. This is an equation of a circle. How? We know equation of circle is for on xy plot is x minus a whole square plus y minus b whole square is radius r square. If we compare these two equations, and what we observe is if we change x coordinate to sigma n, y coordinate to tau, then this represents an equation of a circle with center at a 0 coordinates and radius r. So simply one thing is clear. For this the coordinates are sigma n along x-axis or along abscissa and shear stress tau along ordinate, and this is the origin. Then the center will be represented as m and will be at coordinates a0. A value is sigma x plus sigma y by 2. We substitute a value. Center m will be always at sigma x plus sigma y by 2 comma 0. This 0 means it will be always on the x-axis or the abscissa, or say it becomes m becomes somewhere here. This is the center position. We will calculate like this. Then calculate radius. Substitute value b here. B is sigma x1 sigma y by 2. Then radius becomes this square root of sigma x1 sigma y by 2 whole square plus tau naught square. Sigma x is given, sigma y is given, tau naught is given with proper sign conventions. We know the radius. At that radius, here I am drawing a rough circle. You make a circle with that radius r. So this blue circle is the Mohr's circle or Mohr's stress circle. This is Mohr's circle. Mohr's stress circle. Only thing is when you take suitable scale along sigma and tau, or means along xy axis. Now for the given point A, B, C, D with the given biaxial stress system sigma x, sigma y and tau naught, all positive for the given directions. If a direction changes, stress direction changes, take negative. Then find out Mohr's stress circle center. For Mohr's stress circle center M at sigma x plus sigma y by 2 comma 0. Say sigma x was positive 100, sigma y is positive 50. So it will be 100 plus 50 by 2, 75 0. So for that case it will be 75 0. And radius and say shear stress is 50. 100 minus 50 by 2 whole square plus 50 square. We can solve and we can find out radius. Another sign convention is the same as discussed. Now for horizontal plane CD, we know the stress is sigma y is tensile and shear stress is negative, because for any point inside it is making an anti-clockwise couple. Then according to sign convention, if shear stress or shear multiplied by area shear force makes anti-clockwise couple, it is taken as negative. So stress for plane CD horizontal, which will be the same for AB, or again horizontal plane passing through infinitesimally small point, will be sigma 1 minus tau naught. We will take these forward and construct the Mohr's stress circle in the next slide. Now for the construction, draw abscissa segment or x-axis segment and ordinate or y-axis is positive tau. This is the origin. Now we know the m coordinate sigma x plus sigma y by 2 comma 0. 0 means it will be always on sigma n axis. So taking this distance as sigma x plus sigma y by 2, you locate position of m. So center of Mohr circle is located. Radius is, we will calculate, it will be sigma x minus sigma y by 2 whole square plus tau naught square. So by taking a suitable radius, and now for both sigma and tau, you will take, for both the axes you will take same scale, means 1 centimeter will represent say 20 megapascal. You may take 10 or 15 or any suitable scale as per your given problem. Now by taking suitable radius representing that stress value as calculated, you draw a circle. This circle is known as Mohr's stress circle. For this circle, the rest terms will be explained later. Now we have found stress for a plane CD, horizontal plane is positive sigma y and minus tau naught. So these stress coordinates will be represented as a point. Plane in actual point ABCD of material is here represented as a point PCD. Now PCD coordinates are this sigma n value is sigma y and shear stress value is this tau naught taken downwards because it is negative. So its coordinates are sigma y minus tau naught. So in this way we have constructed a Mohr's stress circle and is helpful to us in finding the different stresses graphically. Now how to find out principal stresses from the Mohr's circle. On the Mohr circle boundary, we observe that there are 2 points P1 this and P2 for which the tau value is 0, shear stress is 0. It means these 2 points represent principal planes. P1 and P2 represents principal planes, and the stresses on these are principal stresses. For example, the stress on this will be sigma n1, and stress on this will be sigma n2 direct stress, and shear stress will be 0. Now, how much will be sigma n1? You measure this distance OP1 in centimeter, multiply by a scale factor, it will give us the stress in megapascal. So sigma n1 maximum principal stress is OP1. From the figure, OP1 is OM plus MP1. MP1 is MPCD equal to radius. Substitute as radius. Substitute the values of OM and radius. We get sigma n1 value. Sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau naught square. Similarly, for point P2, stress is sigma n2 is equal to direct stress is sigma n2 is minimum direct stress, it is OP2. So sigma n2 is OP2. OP2 is now OM minus MP2. MP2 is radius. OM minus MP2 or OM minus MP2 substituted as radius. Again substitute value of OM as sigma x plus sigma y by 2 and substitute this, substitute radius. Only difference will be the relation will be the same. Here we will have a minus sign. If you remember, these two relations are the relations for the principal stresses. Once we take positive sign to find out maximum direct stress or principal stress, and then we take minus sign to find out the minimum principal stress, and are the same as for analytical. One thing more is to be observed is, we know between the principal planes the angle is 90 degree. But in the Mohr's stress circle or in the graphical method, this angle gets double of that. This difference is there between the on the actual point or between the actual planes. The angle was pi by 2, but here it is twice. So what we can do is, you can measure this angle. This angle gives the now position of maximum principal stress plane P1 with respect to PC2. But observe that we will prove later on, this angle will be here twice to theta 1. So you measure this angle, then theta 1 will be half of this. So theta 1 will be position of principal plane. 1 will be at half of angle between P1, M center and PCD. This we will prove in the coming slides. So if you believe me, by simply measuring OP1, we know maximum principal stress. By measuring OP2, we know minimum principal stress. By measuring this angle, we know the position of plane P1, and we will take half in the actual angle theta 1 will be actual between the planes will be half of this. Similarly, taking half of this angle, we know the position of P2 with respect to PCD. Now, maximum shear stress. We observe that there are 2 points which represent corresponding planes in the actual point under stress P3 and P4, for which the y ordinate or y axis or y coordinate or ordinate is maximum. For this it is maximum positive, which is equal to radius. Similarly here it is the value is the maximum but sign is opposite, so it means these are maximum principal stress planes. So for this, normal stress will be sigma n3 and shear stress will be positive and will be tau 3. So for this plane, this will be sigma n4 and shear stress will be tau 4. So tau 4 will be negative and these will be maximum shear stress. So simply direct stress is this much is equal to OM and maximum shear stress is for P3 plane MP3 and for second MP4 and is negative. So MP3 and MP4 are radius. So tau 3 maximum shear stress for third plane is positive R. Substituting the value of R, square root of sigma x minus sigma y by 2 whole square plus tau whole square. Tau 4 is minus R. So same relations. So maximum shear stress is plus minus tau 3 4. We know. Similarly, the direct stress on P3 is sigma n3 and for P4 is sigma n4, and these values are equal to OM. So it is equal to OM. OM is now sigma x plus sigma y by 2. We substitute this, we know the direct stress. Moreover, this M is at the mean position of the two principal stresses P1 and P2, because these stresses are sigma n1 maximum direct stress and shear stress is 0 for this principal plane. For this is minimum sigma n2 and shear stress is 0. So this is at the mean position. So simply direct stress on maximum shear stress planes can be taken as mean of the two principal stresses sigma n1 and sigma n2. So these relations are same. As discussed for maximum direct stresses of principal planes, for maximum shear stress planes also there is the angle between these two is pi by 2, but in the most stress circle it will be double of pi by 2. Now say we want to locate the position of P4. So P4 maximum shear stress plane is, we will measure this angle and then take its half. So basically in the Mohr circle this angle will be double. It means now what we observe is we will measure 2 theta 4, take half, we know theta 4, so we will know that maximum shear stress plane P4 with sigma n4 and tau 4 stress values as anti-clockwise at an angle theta 4 then PCD. Theta 4 is half of this measured. So proof we are doing the next slide. Now for any plane PKL, oblique plane, as we discussed for analytical PKL subtending an angle theta, thus direct and shear stress are sigma n and tau. Now this PKL in the figure is subtending an angle theta anti-clockwise with the CD plane. Here we will take it to be double. Let these angles are this is alpha, this is beta. Then if our concept that angle gets double to theta is okay, then the stress on PKL is represented by the stress coordinates for this point PKL. So these coordinates should represent sigma n and tau. Now sigma n for present case is equal to On positive and tau is minus n PKL. We will measure this, and if it comes out to be same as for analytical, so we will say that this concept of taking this double angle to theta is okay. So sigma n is coordinate for this along sigma n axis is this On positive, and along y axis along tau is this NPKL negative, downwards is negative, minus NPKL. So sigma n is On, sigma n is On. From the figure On is OM plus MN, OM plus MN, and MN is, if we pay attention to this triangle, MPKLN, MN is base, so MN base is, if this MPKL is radius R, so it is R cos beta. We substitute. So sigma n is OM plus R cos beta. Another, this angle beta is total angle pi minus alpha minus 2 theta. So beta is pi minus alpha plus 2 theta as observed from Mohr circle. OM is the sigma n coordinate of center of the circle, so it is sigma x plus sigma y by 2. OM is sigma x plus sigma y by 2. KOM, this is KOM. From this triangle QPCDM, this is radius, this is base, QM is base, it is R cos alpha, and this is perpendicular, so tau naught value is R sin alpha. So QM is R cos alpha, tau naught is R sin alpha. And another, this QM is, this distance is OM minus OQ. So QM is OM minus OQ. Now we know the coordinates for this were sigma y and stress was minus tau naught. So from this OQ is sigma y. OQ is sigma y. We take these observations from the Mohr stress circle to the next slide and derived the relation for direct stress on an oblique plane sigma n. So as per previous slide, sigma n is On is equal to OM plus R cos beta. We substitute value of beta here. We get this relation. Now R cos pi minus alpha plus 2 theta is minus, so this relation becomes OM minus R cos alpha. We open this up, we substitute value of OM, we open it up, so this becomes minus R cos alpha cos 2 theta R sin alpha sin 2 theta. Value of OM is sigma x plus sigma y by 2. Now this is r cos alpha. R cos alpha is qm and r sin alpha is tau naught. As we have observed from Mohr's stress circle, qm is r cos alpha, tau naught is r sin alpha. So we have substituted. Then qm is om minus oq. So let us substitute this. Then om is this value, we substitute here, and oq is sigma y, we substitute here. When we solve, the relation becomes sigma n is sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta plus tau naught sin 2 theta. Same as for analytical method. It means the concept that the location of a plane can be found out by taking double of the angle and locating the point which represents the same stress. Now let us prove for shear stress also. Now, as we discussed, shear stress on this is sigma n tau. Now tau is minus n p k l. So sigma this is tau is minus npkl. This is npkl minus. So tau is minus npkl. If we pay attention to this triangle m and mnpkl, this mpkl is radius, this is perpendicular, so npkl value will be r sin beta. So npkl we substitute as minus r sin beta. Rest are the observations same as we have taken in the previous slides. Let us take it forward and find out the value of tau minus npk. So it becomes r sin beta. You put value of beta, so it becomes like this. Sin pi minus alpha plus 2 theta is sine of alpha plus 2 theta. We solve this, we get this relation. We open it up. Now r sin alpha is tau naught, r cos alpha is qm. As we have observed, from r cos alpha is qm, r sin alpha is tau naught. Now qm is om minus oq. So you substitute, or we substitute like this. Now om is this sigma x, om is this, and oq is this. We substitute and we solve and rearrange the terms. Tau becomes minus sigma x minus sigma y by 2 sin 2 theta minus tau naught cos 2 theta. Same relation as for analytical method. So we have studied about Mohr's stress circle, which helps us in finding out principal stresses, location of principal planes, maximum shear stresses, location of maximum shear stress planes, and direct and shear stress on any oblique plane subtending an angle theta with the horizontal plane. Only thing is, angles as represented in Mohr's stress circle are double than the actual angles. Thanks.